Hey, good afternoon, everyone. Hope you guys doing all right today, this fine afternoon. So now let's get started. So last class, we learned that when we put something in a fluid, and what happens? It experiences net upward force. That net upward force is called buoyant force. And we denoted buoyant force by FB, and that buoyant force can be written as volume of fluid displaced by the object. It's not the volume of the object always, okay? Not always the volume of the object. That is case only when object is totally inside the fluid, okay? So volume of the fluid displaced by the object times density of the fluid displaced by the object times G. In other words, mass of the fluid displaced times G. And that came from the Archimedes principle, right? So we learned that. So now what happens? When we put something in water, it sinks. Sometimes it does not. Some other object may not sink, okay? So even tiny needle, when you drop in the water, it goes all the way down. Tiny coin, let's say a quarter or even cent, when you drop that penny, I think that's what we call it, right? When you drop in the water, what happens? It goes all the way down and settles the bottom. But when you have a wooden block, when you put that in the water, even if it is big, what happens? It doesn't sink. It just floats on the surface, partially inside, partially outside. So why some object, even if it is very large, means it has large weight, can float, but tiny object like this can sink? So yes, just like Christian indicated, it's a density, right? So ice can float, but the metal like this can sink. And there is another puzzle. These big cruise ship, they are made up of metal and they don't sink. Otherwise, we wouldn't be booking cruise. Anyway, this is not time for booking cruise, right? In this virus situation, anyway. So anyway, yes. So how do we determine that? So it depends on density. So let's prove that, okay? We prove it. We don't just say, okay, my gut, okay? My gut is telling that. We don't say that in science. We try to prove it, okay? So one, you do experiment. Another one, prove it theoretically as well. Better, do it both ways, okay? So there are two forces acting, competing force. Weight is pulling down, try to make it sink, and buoyant force is up. It's pushing it up, not letting it go down, right? So there is, tug of war between these two forces. So it boils down to net force, right? If mg is larger than fb, then what's going to happen? It's going to sink. If FB is larger than mg, it's going to float. So let's write down net force in terms of density, okay? So mass is density times volume. O here means object, okay? Object that's in fluid, and F is fluid. Buoyant force, we just wrote that down, right? So let's plug that in that equation, so that becomes net force in terms of density and volumes. So now we can have two situations, float and sink. Is something going to fly off from the surface of the water on its own with just these two forces? No. So there is just, float and sink, right? Two situations. So if it is synced, when it is synced, or when it is inside, when it is immersed, what happens? Volume of fluid displaced is equal to volume of object. So because of that, what happens? Yeah, G is same always. So these two are also same. Remember, when is that case? When they are immersed. When object is immersed. Okay. So now what do we see? So when object is immersed, that means net force must be down, isn't it? Here, net force must be down. Object is immersed means net force must be down. So depending on which way we choose positive, right? So Fi has to be positive or negative. And here we are writing FB as a positive, means we are choosing up as a positive Y, right? That's what we chose. So that means the F net is down, or I should say negative. So when do we get negative from these two numbers? So if I have, let's say, rho F 8 and rho 0, 10, 8 minus 10 is negative 2, right? So that's when I get negative. So that means density of object has to be larger than density of fluid. Okay? So object sinks when it has larger density. And we know metals, they have larger density, like more than 1,000 kilogram per cubic meter, and water has just 1,000 kilogram per cubic meter. So density of metals, they are larger than density of water, means they can sink. Doesn't matter the shape. I mean, even tiny object can sink. Even a penny can sink as long as it is made up of metal, and I think it is, right? So now, so let's say you put that object, it's trying to, let's say it's inside, but density, when density of fluid is larger, for example, density of water is around 1,000, and density of wood is around 800. So what that means density of fluid is larger than density of object, means wooden object here. So in that case, what's going to happen? Net force is going to be upward. Net force upward means even when you leave that object, bring that object, push that all the way down in the water and let it go, what's going to happen? It's going to accelerate up and going to come to the surface. And as it starts coming out from the surface, net force becomes smaller. Why? Because the volume of the object is no longer equal to the volume of fluid displaced. in this case. Fluid displaced becomes smaller than the volume of the object because only part of the object is now inside the water. And volume of the fluid displaced is simply only the part of the volume of the object that's inside. So part of the volume of the object that's inside is going to be always less than object's volume when object is not fully immersed. Okay. So what happens? It's going to just keep on coming up until that volume displaced becomes small enough to make this buoyant force equal to the weight of the object. And that's when it goes in equilibrium. No net force, no net upward, no net downward. That means it's just floating on the surface, and part of it outside, part of it inside. And how much inside, how much outside, again, that depends on density of the object. And you can calculate that by using this equation here, okay? Did I write that equation here? Yes. So now, let's suppose I want to solve for volume of the fluid displaced by volume of the object here from this equation. So that means I am bringing that one there, means, right? So what fraction of this gonna be outside? See, this volume of fluid displaced is equal to volume of the object that's outside, sorry, inside. Oh, so that means what fraction is going to be inside? What fraction of the object going to be inside? So let's say this is object and this is water. My hand, this hand is water, right? So that means this is outside fraction, this fraction is outside, and this fraction is outside, and this fraction is inside. So now, right now, outside is less than inside. So if that fraction is 2/3, that means 2/3 is inside, 1/3 is outside, okay? And that is determined by the ratio of the density of the objects. So if you know the density of object and density of the fluid, you can tell what fraction of it gonna be inside, what fraction gonna be outside when it is just floating, okay? And to float, density of object has to be less than density of fluid. Okay, so that's the thing. Yeah, it's a very busy slide, but those are the things it's talking about. All those are related. Okay, so now we can make use of that and calculate. So for example, let's suppose if you don't know density of something that can float, you drop that inside the water and find what fraction of the volume is inside, and with that you can calculate the density of object if you know density of fluid. And if you are using water, you know its density, right? So that's how you can practically find density of objects, okay? So even if the object does not float, then what you can do is you can hold it inside and measure how much force is there now you are using to hold it. Once you measure it, what you can do? You can do the calculation, some calculation to find the density. And you'll see one example there soon. But before we do that, let's answer this question. And you have 1 minute and 30 seconds to answer this. 30 more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Let's see what we got here. So less than the density of water. So if it was equal, then it would be floating barely outside. Most of it would be inside. Wherever you leave, it's going to be there. Okay, if equal. If it has a larger density, we know it sinks. What object floats? The object that has smaller density and that can float. So that's why B is the correct answer. Yes. Okay. So that's how the boats, for example, cruise ship, they are made up of mostly metals and wood. So what happens? There is a lot of empty space filled with air. So on average, the density is going to be less than the density of water. So that's why the cruise ships can float in the water. Okay. And see, this one has a density way smaller than the, looks like the average density is way smaller than the density of water. How do I know it? Because it's floating all the way top. Only small part is inside. So the density, average density is way smaller here because we know density of air is way smaller compared to the density of water. So although the human had, the density, let's say whole body density is slightly more. It's because of the head, okay? Head has a higher density of water than, head has a higher density than the density of water. The other body part, not much, okay? So that's why we can float if we know some skill to keep our head high, okay? On the other hand, ice is made up of water. It has slightly lower density. So when there is iceberg, what happens? You can only see some tip of the iceberg. Most of the ice is inside. So that's why, unfortunately, Titanic happened, right? So although on the top it was small, it wasn't visible from the very far. If it was big, I guess it would be, if it was big outside. But although it was small on the top, big down there, it was really big. Okay, I mean, when inside the water, it was really big. So that's why it kind of, after collision, whole boat went something like that based on what I saw on the TV. I wasn't in Titanic, by the way. Okay, so here is question for you. And you have a minute to answer this question. Thirty more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see what we got. Hey, it looks like nice steps from the right side. You hop into the C and then onto the B and to the A. You reach higher. Okay. So let's suppose I am thinking A as the correct answer. Why am I right or wrong? Okay, I see hand. Go ahead.
Hiya, yeah. So I'm thinking that A is the wrong answer in this case. And I'm going to say that because the buoyant force is always acting against the gravity, right? If we had more water, the buoyant force would just keep on going up, right? The only thing stopping it is the amount of water that it's at. So that's why I say that B is the right answer.
Buoyant force is always bigger. Okay, that makes sense. Let's see what other think.
I think A is the correct answer because if you draw the free body diagram, the buoyant force and the weight force are acting in opposite directions. And if you set up as the positive, and then you say the sum of the forces on the Y is buoyant force minus weight force, and the sum of the forces is going to be 0 because there's no acceleration, so then there's no net force. And we know there's no acceleration because it says it's motionless. And then you can just rearrange it and you get mg equals fb. I don't know if that was confusing, but
Hey, looks like I need to change my mind. That makes sense. Net force is 0. It's in equilibrium. So that means upward force, downward force must be equal, right? So, yeah. So it is the correct answer. So now, let's find the density of dog. And you can use this method to find density of any object, okay? So if it's not sinking, then net force is going to be 0. You can easily find density. But even the object sinks, what you can do is you can tie that object in a string and use a scale. For example, in this case, you are weighing a dog on the air and you find that much weight. And weight means mass of the dog times g, right? So whole mg is given, not just m, but mg is given. And of course, if you need, you can find mass of the dog because you know g means you can calculate it. Now you repeat the same thing. Now this time, what's happening? Dog is inside. And the reading is 22 Newton. So it went from 220 to 22 Newton. So that means the buoyant force must be the difference between these two, isn't it? So why reading is changing? Because we are getting help from the buoyant force. So the difference is the buoyant force here. And we can show that by making a free body diagram. So in this case, it's asking for the average density of the dog. So where gonna be the dog's density? Where can we dig so that we can find the density of dog? We know you know, like density, mass, and volume are related. So maybe we can write something like that. Density of dog is mass of dog divided by volume of the dog. Hey, mass of the dog we can find from here. So now we need to look at, or somehow need to find, volume of the dog, and that's going to be equal to the volume of the water displaced by the dog when it's inside. And that volume of fluid displaced is related to buoyant force. And that buoyant force is the difference between those two waves. So that's how we need to relate all those things, okay? So here, since, you know, weight of the dog is given, we can just write something like that rather than just writing mass, right? So if I do G here, I can do G here as well, multiply by G up and down. So that means, you know, it's same thing, right? It's just a little mathematical trick there. So we know that means we need volume of the dog to find density of the dog. So just like I said, volume of the dog is equal to the volume of water displaced because dog is inside the water when we are finding its new weight. So can you draw a free body diagram? So dog is being held on a scale inside the water. Are you guys drawing the free body diagram? I know how to draw a dog. We are interested force acting on the dog. So that means I can draw a dog as a dot, right? And mg of the dog gonna be down there. And what forces are there? Hey, it's in the water, must be buoyant force. I can tell. And what is this? What direction that force is acting? Up or down? Is it up or down? Yeah, it is up. So now when we are holding dog inside the water, that's what's happening. Okay, that's how the free body diagram looks like, okay? So that means we can use equilibrium condition to find buoyant force. So buoyant force plus tension or scale reading is equal to, oh, yeah, that's equal to mg, but let's write this down like this. And FB is gonna be mg positive and T negative. A lot of buoyant force. mg is 220 minus tension is 22. Hey, is that 198? Yeah, it looks like 198 Newton. That's the buoyant force. Okay, we found the buoyant force. Now, where is the volume of dog in the buoyant force? Can we find volume of dog from the buoyant force? We know buoyant force is volume of fluid displaced, density of fluid displaced times G, right? So that means, hey, what do we need? We need this, both. VD times G. And we know volume of fluid displaced is same as volume of dog in this case, because dog is inside the water. Okay. So this means volume of the dog we can find now because we already know FB. We know the number, right? But since our equation, this equation, original equation where we have density of dog, that's what we are looking for, means we need both of that. So why bother dividing by G? Just leave it G right there, right? BdG. So that means it's going to be buoyant force divided by density of fluid. And what is buoyant force? 198 Newton. And what is density of fluid? 1000. Now, so this thing looks like it's going to be 0.198. So now we can go all the way up here and say, okay, this thing is already there. So let's write that down. And this one we just found here means we can write that as a 0.198. So dog is inside water, dog is sinking. That means density of dog better be larger than density of water. We're not calculating density here. Oh, we know density of water is 1000. So are we getting larger than 1000 number here? Density of dog must be larger because it was sinking. Okay, and we hold it by attaching a string and scale, let's say. So better be larger. And looks like it is larger. And shouldn't be very large though. And I don't know if this is real numbers, but anyway, yeah, I can tell that number is larger than 1000. So are we getting somewhere 1100 or something like that? Yeah. Hey, 11111. Okay. Yeah, that sounds reasonable. 1000 versus 1100. Okay. Okay, so now here is this question for you guys. And you have total 1 minute to answer this question. And I forgot to warn. 15 seconds. 5 seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see what we got. C and sinking versus floating simply depends on density, not on weight. Yes. So that's why, what happens here? Balloon. Why we need heated balloon to float? Why cannot just an air balloon can float without heating the air? So when you heat, what happens? The air molecule goes a little further apart. So density becomes smaller. So density of air inside now becomes less than density of air outside. So now that means what happens? Density less means it can float, okay? And if density becomes really small, then it can even shoot up, okay? So that's the reason, okay? And these boats or, you know, these ships, what happens? They go inside the water until their weight becomes equal to the weight of the water displaced. So that's why it does not just stop there, but it keeps going until this volume becomes large enough so that the weight of it becomes equal to the weight of the whole system, okay? So here you see buoyant force is small. Why? Because it's displacing a small amount of fluid. Here it gets a little bigger, but it's still not enough to balance it. Oh, looks like I need to draw a little longer there. Okay, so now when this becomes equal to this whole weight, that's when it is in equilibrium. Just like the wooden block was floating when buoyant force was equal to the weight. Same thing, anything that's floating in a fluid, what happens? That condition has to hold, okay? Because it's in equilibrium. So now here is a question for you. And you have 1 minute and 30 seconds to answer this question. Thirty more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Oh, I see there is demand for heady stand. So even one wrong answer, you don't get heady stand. That was the rule, okay? And let's see, how did we do here? A lot of wrong answer, no matter which one is wrong. So I saw somewhere it said I did not choose the correct answer. Is that right? I thought I did. Okay, so now is B has a lot of answer. I'll go with B. But can somebody convince me why that's the correct answer or not?
So I believe B is the correct answer because you're looking for the buoyant force on the balloon. So you'd be measuring the density of the air that's inside the balloon, which is a helium, not the air that's outside the balloon.
Okay. Density of the density inside.
I disagree.
Okay, go ahead.
I think that this problem is similar to a wood block and water problem. We're measuring the buoyant force is measured by the amount of air that's being displaced in this fashion, right? And whether or not the amount of air that you displaced is heavier or lighter than the amount of material that you replaced it with, right? So in this instance, I'm considering the helium as a block of wood and the air as water. So I would need to use the air as the buoyant force, not the helium.
So that's the definition of buoyant force. Everybody agrees on that. Is that correct? So in this equation, it says, so volume of fluid displaced versus object, they are same, both are same here. So let's forget about that. Now it says density of fluid. And both helium and air, both are fluid, right? So that's what causes confusion here. Now, the question is, here, we need to read something like, is the density of fluid displaced? Read that as the density of fluid displaced. So what fluid is being displaced by the balloon system here? Helium is part of the balloon. It's the air that's being displaced. Okay, so that's why it has to be air, and it is the correct answer. Yeah, unfortunately, folks, a lot of you got it wrong. Okay, but that's the correct answer here. Okay, so now let's go for flow. Okay, rather than just floating and sinking, let's move. Okay, let's talk about moving fluid, flow. Okay, so fluid flow is very complex phenomenon, but some of the fluid flow situations can be described using simple mathematics. Okay, and that is this kind of flow, this kind of flow, this kind of flow. Yeah, so it has to be some controlled situation, but we can obtain that. So for example, when water is flowing through a pipe, and especially when pipe is horizontal, then we can have this kind of situation. Even if it is inclined pipe and water is not flowing really fast, we can have this kind of situation, okay? If water is flowing in a river, that's a kind of calm river, okay? And then we can have this kind of situation, okay? So these are called streamline, and also there is another name for that, okay? Lamina, because they look like one layer of fluid over another layer, okay? So when we have this kind of flow, we call streamline, laminar, like that. But we may have laminar flow, and soon, that may get converted into turbulent. This one, no, we cannot analyze that here in this class. This one, yes, we can. And that's what we're going to be focusing on, okay, in this chapter. Okay, let's talk about motion, flow. So speed here, let's say. So to make things simpler, let's assume we have cylindrical pipe, and inside the pipe, the water is flowing. So we can just look at the section of the water, column of the water, and follow its movement, okay? Let's follow the movement of that particular column of the water inside a pipe. It has a shape, cylindrical shape. So area is A, cross-sectional area is A. That's going to be about the same of the inner diameter, right? So this diameter of this column is going to be same as the inner diameter of the pipe. And pipe is not thick. We can say, okay, the area of the pipe is about the same as area of the fluid column. Okay, we can say that. And now, let's suppose fluid is flowing with speed V. That means in a given time, it's going to travel through a distance, delta x, right? So that's one way to look at it. Another way, so when you capture that column of water and weigh it, then you can write the mass of that column of the water as a density of water, or if it is different fluid, it's the same thing. Density gonna be different, but the equation gonna be same. So density times volume is the mass. And in this case, you see this delta because we're not talking about all the mass that's coming out, all the volume. We are just talking about volume of particular segment. For example, just from here to here, let's say. So when you collected that water, let's say you just collected this much and you stop the faucet, okay? So that means you can write like that. And the volume is area times the length. So I can write like this, okay? So that's the volume of the column of the water. And this being the distance traveled by the water column. So if its speed is V and time it took is delta t, then I can replace this delta x by V times delta t. Okay. Now what I can do is I can rearrange this. So this delta t, bring it down here. So it's going to be delta m over delta t. So mass you are collecting, let's suppose you open the faucet. Now you are measuring how much mass of the water you are collecting over certain time interval, right? So let's suppose you collected water for 5 minutes and you weigh it. You divide the total mass by the time, that's gonna be the rate of flow of water. Rate of mass flow of the water. So flow can be in terms of volume flow or mass flow. So in this case, this is mass flow, okay? So rate of mass flow. So that means this is rate of flow of the water. So we can write something like that. Delta m over delta t is the rate, and that depends on 3 things: density, area, and speed, okay? If flow is constant, let's say, whatever goes in and that's coming out through a section of the pipe, that means flow rate is constant. If that's the case, then in that case, what may happen is that if the pipe size is different, then its speed can change because, see, the speed, area, and since the density remains about same, water does not get compressed. What happens? How fast it moves depends on the area. But if it is a gas, then density may also change. So we may have two kinds of situation. So let's write flow in the flow of fluid into the pipe at this end, and flow of the pipe, fluid getting out here, okay, at two different areas. So let's write it down, okay? So flow at point 2 is that, and flow at point 1, I can write like that. So all subscripts are 2 for the point 2, and all subscripts are 1 for point 1. Only that's the difference. Otherwise, it's just this equation, right? Now, flow rate, same, because what goes in, that has to come out unless there is source and sink. We are just talking about fluid flowing in a section of pipe, okay? So that means this and that must be same. Flow rate same means they must be same. This equation is called equation of continuity. So this is like a kinematics of fluid flow, okay? This is like a kinematics of fluid flow. So I'm writing this for a case when the fluid is basically liquid. When we have a liquid like water, the density does not change, means density remains same, okay? So that means the density cancels if they are same, right? When they are same, they cancel, means we have equation of continuity like this. The speed depends on area, right? So this is winter. We don't water our garden, I think, but if you have used water hose, garden hose, right? So what happens if you block part of the pipe, water comes out with higher speed and it lands farther. And it doesn't have to be garden hose. You can experiment that in your sink faucet, okay? So what you can do is let it run nicely, nice stream, and block part of it. What happens? It's going to start coming out faster, okay? So that's what this equation is telling you. When area is smaller, or even better if I write like this, AB constant, okay? See, A1, B1, A2, B2. Product of A and B constant means when one of these goes up, another one comes down, and vice versa. That's what it means. Understand that. Understand the meaning of this equation here, okay? And we can also write flow in terms of volume rather than mass. So what happens? Volume flow rate, we denote that by uppercase Q usually, okay? But it is basically how much volume is changing with time, or how much volume of the water you are collecting over time. So let's suppose you are, like collecting water from the tap using a graduated flask or cylinder, okay, or measuring cup. So you collected it for a few seconds and you have now volume. Divide that by time, your volume flow rate, right? So just like mass flow rate is same, we can say volume flow rate gonna be same as well. And what is the volume? Volume is area times the length of the column it passes through. So we can write like that. At one side like this, another side like this. And when we divide that volume by time, that gives you flow rate, and you get the same thing. So now this length divided by time, or displacement of water column over time, is the speed. It's the basically same thing. Either you look in terms of volume flow rate or mass flow rate, you get the same continuity equation. But keep in mind that if you have gas, then you need to use this, where density is changing. When density is changing, you use this equation. When density is not changing, you use this equation. And this is, just like I said, this is like a kinematics of fluid flow. Okay, simple, just one equation, kinematic equation, okay, not three. So now here is a question for you. And you have 1 minute and 30 seconds to answer this. Thirty more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, well, let's see what we got. We got mostly B and C. Hey, it's the continuity equation that's pulling the water, isn't it? Wait a second, equation doesn't pull water. Nope, I think B makes more sense, okay? It's the gravity that's pulling water. And because of that, it's speeding down. It's freely falling. Speed is increasing. So when speed goes up, area goes down. Okay, so that makes sense. Okay. Looks like it's a break time. So there was this news, okay? So we'll talk about this after the break. Meanwhile, if you like, you can read the slide. Okay, so this is gonna be the work done. So the product of pressure change and volume gives you the work done. So there is pressure in this equation, but what we want is, we want speed in the equation as well. So how do we bring speed in this equation? So for that, we need to go back and look at the relationship between work done and energy, right? Work and energy. So work done can be written as change in, kinetic energy and change in potential energy, okay? So now change in kinetic energy means final kinetic energy minus initial kinetic energy. So we need to label which one is initial, which one is final. So let's say this is initial point, okay? So this is initial, and this is final. So this yi gonna be initial height, and y2 gonna be final height, okay? So now we can write kinetic energy and potential energy. So kinetic energy we know is half mv square. So when we write mv1 square, that means it's the kinetic energy here, right? When we write v2 square, that means it's going to be kinetic energy there. So if it's going like that, so it's going to be final, and this is going to be initial, okay? Like that. So this is change in kinetic energy, and this is change in potential energy, because it is UF, this is UI, this is VI, this is VF, final minus initial, and so on. So why this water has to be pushed? There must be some sort of friction, okay? So it's like work done by non-conservative force equation I'm using. In our formula sheet, we had like WNC, okay? So that work done and this work done, they are same, okay? So for that reason, I am skipping that ENC, but that's what that is, okay? So now, they are same means right-hand side of this equation and right-hand side of this equation must be same if left-hand sides are same, right? So I can write like this. I see mass, I see volume. And I also know mass divided by volume is density. So what I can do is I can divide both sides by V, means I need to divide all terms by V. And B here being the volume. Uppercase V is volume, lowercase b, they are velocities, okay? So what happens? Mass over volume is density. So I can replace all masses by density. So volume from this side is gone to this side and made all masses or changed all masses to volume, sorry, density. So half mv square kinetic energy. What is half rho v square? We can say that's the kinetic energy density, okay? But don't worry about the term here, okay? So we are almost there. So there is a relationship between pressure and speed. That's the dynamics. Change in speed is acceleration, right? Change in speed, net force is equal to mass times acceleration. That's what Newton's second law is. So this is like a Newton's second law for the fluid flow. It's in terms of pressure rather than force. So we have density instead of masses. Okay, so what I'm doing is I'm just bringing all the terms that has one subscript in one side and one with the two subscript in the other side. And the one with the two subscript, all of them have, I mean, this P2 has a negative sign, so when it goes to other side, it becomes positive. And similarly, on the other side, all the terms that has one subscript, they have negative sign. So when they move to the left side, they become positive. So that's why all terms are now positive, and all of them are in left side, all of them are in right side there with the subscript 2. So just like we had rho 1 V1 is equal to rho 2 V2, that's like a kinematics of the fluid flow. And we wrote that as a rho v is equal to constant. Similarly, when we have repeated term, we can just write, equation as this equal to constant. and get rid of all the subscript or superscript in that matter. So probably you may have seen this kind of equation in your chemistry class, and we'll write that one here as well in another chapter, okay? And that can also be written as PB over T is equal to constant, okay? So we can do that. So that means I can write condensed form of Bernoulli equation like this. Okay, so sum of those three terms remains constant at each point. Okay, so that's what that equation is telling us. Now, how do we use it? How do we use it to explain flow phenomenon that we observe in our daily life? So that's what we want to do, okay? So here, the y is the height, change in height, right? See, if height is not changing, that means we don't need to worry about y thingy. Just like when height is not changing, we don't need to worry about gravitational potential energy. And basically that's what it is. It's written in terms of density. So if we have a flow, just horizontal flow, that means this equation just becomes, these two terms is equal to constant, okay? If pressure is not changing, we don't need to worry about pressure, and so on. So that's how we're going to be writing this equation. So let's suppose this plane is flying. Oh, not flying yet. It's just running on the runway to take off. Why planes have to run, go through very high speed before they can take off? How do we explain that, right? So let's take a look. So when it is just running on the runway, its height is not changing. So is the plane fluid here? It's not. What is fluid? It's the air that's flowing from the top and bottom of the wing. And the wing is set such a way that the speed is higher on the top than on the bottom, okay? So since height is not changing here, it remains, you know, the fluid flowing just horizontal, means we can forget about y, and I can write like this. So now, what happens here? When it's moving, when plane is moving really fast, this way, air is flowing this way, right? I may have drawing here, yeah. So now, the speed of the airflow from the top is faster, way faster than the speed from down. So now, let's take a look. When speed is larger, pressure has to be smaller. See, the sum of two is constant. So it's like saying, okay, 4 plus 8 is 12. And constant means the 12 remains 12. That's what constant means. The right side is not changing. Now, so here we are saying on the top, V is larger, right? So that means when V is larger means when this term becomes larger, means when, let's say, 8 becomes 10, for this to remain 12, you need just 2. So that means 4 decreased to 2. This term decreased when this term increased, okay? So when this term went up, became 10, this term went down, okay? So same thing here, when speed increases, means this term is increasing. It's larger, means P has to be smaller because this side is constant, okay? So that means pressure on the top of the wing is lower and bottom is higher. So higher pressure from the bottom, lower pressure from the top. So there is pressure difference. So that pressure difference times area of the wing gives you force, upward force, okay? That gives you upward force, and because of that, what happens? It lifts. It can lift that way. So that's how the plane lifts, okay? So that's why they have to run and get certain speed. This term has to be small enough, okay? Sorry, this term has to be large enough to make this one low enough so that it can take off. So to do that, the plane has to be moving really fast, okay? So larger the plane, larger the lift force is needed. So that's why they have big wing, means area larger. And for larger plane, you need longer runway as well so that it can speed up fast enough to gather larger pressure difference, okay? So that's the application. And now here is question for you. So use what you just learned, okay, to answer this question. And you have 1 minute and 30 seconds to answer this question here. Oops. Thirty more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Let's see what we got. Okay, Robert, what is it? You are muted.
I'm just ready to debate. That's all.
Okay, so you wanted to be fast to respond? Okay, we got some varieties here.
Okay. Yeah. So I'm thinking that it's A, right? Because we have the air that's going in this direction, right? And these will spin, but they're both going this way. I know that much. I'm thinking that much. So that's why I'm thinking A. Thank you.
Okay. Thank you for sharing your thinking. Okay. And but a lot of people seems like they disagree because did not choose A, right? So anybody, please share your thought in this. So we are blowing air in between the cans. That means B is larger in between the can than the outside the can. Is that correct? So yeah, I'm seeing a lot of explanation in the chat. Hope you guys are reading chat. Yeah, looks like it's gonna surprise a lot of you, but yes, C is the correct answer. And when speed is larger, pressure gonna be lower. So the can's gonna move in the direction of lower pressure. And it happens. You can try that at home, okay? Make sure can is not filled with fluid. and yes, you're not doing that in carpet, but doing in very smooth floor. I mean, let's say tabletop, countertop, something like that, okay? Less friction is better. So now let's take a look at this problem. Read the problem. Okay, folks. So that's the change in pressure. So this is change in pressure. So you plug that in over there along with the area that gives you force in on one of the wing. Oh, there is a question. How did we get F is delta P times A? Anybody knows the answer? Force is pressure times area. Pressure is force over area. This is the definition of pressure, right? So I'm writing that from that, okay? Okay, thank you for help. So now I'm gonna move on. Have you guys seen prairie dog like this with this kind of, you know, on the, they collect this, they dig the burrow, and is that called mound? Oh, nice. Okay. And those mounds, if you can find on both sides on the tunnel, you know, mounds on both sides, what happens? You see, one is a bit sharper, taller than the another side. So that means the speed here, you know, like speed on the sharper side, just like we had for the, you know, plain wing, speed larger. Pressure lower, okay? So that means there is lower pressure, means the air can flow through that. That way they can breathe air when they are inside. So that's how they do the ventilation thingy. They are good engineers. Okay. Yeah, next time when you see this, see if you can see. So see, it has to be part of that tunnel there, okay? So there may be another one, another tunnel going on there in prairie, or you know, there are a lot of those. So if you are a life scientist and if you are wondering how come they can survive that whole winter inside that hole, where do they get air from? So that's how they have that ventilation system going on. And in our body, what happens? There can be blood clot. And when there is blood clot, in one side, blood may be flowing faster. And faster speed makes pressure difference, okay? The speed difference creates pressure difference. Pressure difference means force difference, and that can rupture that, okay? So by measuring the speed of blood flow, you can tell if there is clot building or not, okay? If clot is building, you will detect difference in speed in two sides, two parts of the artery or vein, okay? If flow is going smooth, there is no clot, okay? And so before it ruptures. You want to catch that, okay? And of course, we have noticed this stinky thingy there always underneath that sink, right? It captures that stinky thingy, and when it gets clogged, oh, we need to get rid of that, and that's nasty, right? So why do we keep that nasty thingy there? So it turns out that when we are flushing, let's say, a lot of water from our washer, what happens? High speed, low pressure. Okay. And what can happen? Low pressure and high pressure on the top here, that atmospheric pressure. And because of the flow, pressure is lower, means this can just get out from there. Hey, that's a nice thing. It got out, right? Now this whole thing is connected to sewer. Now what's gonna happen? The smell from the sewer gonna sneak into your kitchen or bathroom. Not good, right? We don't want that. So to prevent that from happening, what we do is you connect a bend all the way to your roof, so that what happens when pressure starts getting down, lowering because of that flow, when it's flowing, pressure try to get lower. But if this vent is open up there, it's connected to the whole atmosphere, means pressure remains constant. It doesn't get lower, means this one survives there, means the sewer, smell from the sewer not gonna get to our home. Yes, it keeps the smell down the pipe. Yes, thank you for the help. And that T is Torian, I know that. And this one, my attempt to make it funny or cartoony, okay? But of course, that's not my drawing, but words are mine. So have you ever noticed, if you have this kind of setup in your bathroom, this may just come and try to stick in your body, leg, okay? Okay, I'm getting that haha thingy I like, and it's okay. Thank you for that. So now let's look at the situation where there is no pressure change. So let's suppose you have a tank there, okay? And it is open, means pressure here, atmospheric pressure. Opening here means atmospheric pressure. Pressure is same. So we can just ignore pressure here to use this, okay? So now what happens here is we can solve this equation. So it's a fluid flowing, and fluid is just same fluid, right? It's if it is water tank, it's water here, water there, okay? So now we can solve for the speed, for example, V1, with what speed is going to come out. We can solve that, okay? That. And if it is not flowing at all at the top it is calm, now no flow, then we can set that equal to 0, means it's going to be just that. So it just simply depends on height, okay, difference in height. So it's like a free fall. Here, of course, we are ignoring any kind of, friction between the water molecules, okay? So it's like a free fall, okay? That's how fast things gets moving when it falls through a height h. So we can use that, okay? So let's suppose our county or our area has a water tank that is 21 meters tall, how fast the water going to come out in our faucet, right? We can calculate that. Or if you know speed that's coming out from your faucet, somehow if you can find that speed, then you can tentatively tell what's the difference in height between your faucet and the water tank of your, you know, like, yes, water supply tank of your city. You can tell that, okay? So that's why they keep tall tanks in the city, so that we get fast water flowing through our shower, okay? Not just in the kitchen. And now, so far, we've been assuming that fluid is ideal. There is no friction between the fluid columns, but there is friction. That's what we call viscosity, okay? Some fluid, they can easily flow. Try pouring water, no problem. Milk, no problem. Try pouring honey, flow gonna be really slow, right? So there is friction between these layer. Remember we talked about this lamina? So we can think of one lamina sliding over another lamina and giving some friction. So since this friction occurs not in solid, but we are talking about fluid, we give different name, and it has slightly different property as well. So for the solid, friction between solid is friction. Friction between, you know, fluid lamina, that's a viscosity, okay? So what happens is we may expect to see, you know, same height if it was ideal. But what happens is from one side versus another side, and there, yes, it makes sense if it is, you know, area is small, B large, A small, B large. That means P small, right? So pressure lower means it's going to withstand lower height. Makes sense, right? And now the area, this side and that side, they are equal. So speed should be same, means pressure should be same, this height should be same, but they are different. So what it is telling us? It's telling us the pressure is different, because this height different means pressure is different. So why pressure difference? Although A is same, that means speed must be different. So why speed is different? Since area is not different here versus here, why speed is different? Must be because of the friction, okay? So that's what we call viscosity, okay? And we can explain that by thinking that when fluid is flowing, there are the several layers of fluid just sliding over each other. And all those layers have a thickness of about the molecule of that fluid, okay? And when we have this kind of situation, we can write equation like this, and this is called coefficient of viscosity, okay? This is force you need to keep that thing flowing, and that's the force you saw in the equation we had for Bernoulli equation from where we got the pressure, okay? And this is speed, this is area, upper area of these layers, and this L is how far it is. So for example, think about river. What happens? At the bottom of the river, the water is barely flowing. At the top, it's moving fastest, okay? So that's the effect, okay? And what's the proof? If you look, probably in chemistry lab, when you are doing in-class lab, probably you use Bunsen burner. What happens? At the middle, you see high flame, okay? So these are coming faster at the middle. So flow is faster at the middle, and near the wall, it's not flowing much, okay? It's slower, okay? So that's what it means, okay? So this is called coefficient of viscosity, just like we had coefficient of friction, but the property is slightly different, okay? So now, oh boy, do we have time? Looks like we ran out of time. So here is a video I like to show you. Oh, I'm not doing the polling here. So from this video, probably you can tell what's going to be the correct answer in that case. Similar setup. So difference in height, as you notice here, okay? Larger area, same height right now when there is no flow, but when there is flow, there is height difference, see? Higher height, not so high. Higher where there is faster moving. See, this concentric means V is larger. So that means pressure is lower. So that means it can rise higher, okay? So with that, the D gonna be the correct answer in this case. I'm not polling it because we ran out of time, okay, folks? So I'll see you next week. And I think my office hour starts at 4 o'clock today, and I'll be right here in this Zoom. If you like to talk to me, feel free to come back or stick around, okay?
Thank you.
Thank you.